In this chapter, we're going to cover electrochemistry. So we'll start off by talking about how to assign oxidation states, what is oxidation and what is reduction. We're going to talk about oxidation-reduction reactions. Then we'll get into balancing those same redox reactions. And that's probably where we'll stop in this first half. And in the second half, we'll pick up by what is a voltaic cell and doing some calculations surrounding electrochemistry. First, let's start off by defining a few definitions, or a few terms that we're going to use for electrochemistry. First of all, what is electrochemistry? So electrochemistry is the area of chemistry concerned with the interconversion of chemical and electrical energy. In other words, it's the part where we study turning chemical reactions and maybe the transfer of electrons. We tie that into things like making batteries, electrochemical cells, basically measuring voltages, these kind of things as they pertain to chemicals. So electrochemical reaction. What is electrochemical reaction? This is a reaction where electrons are transferred from one species to another. Okay, so electrochemical reaction, this means we have to have electrons transferring back and forth. Okay, and these are known as oxidation reduction reactions. And for short, we call them redox reactions. Okay, so what is oxidation? What is reduction? So first of all, oxidation is going to be the loss of electrons. Reduction will be the gaining of electrons, or the gain of electrons. Okay, and the best way I know to remember this, there's a couple of ways to learn this. Maybe you learned one of these. So the first one I know is an acronym, oil, and then rig. Okay, so oil is oxidation. You can say is loss of electrons. And then reduction is the gain of electrons. Okay, and the other one I know is this one, Leo. Leo Gur, or Leo Alliance is Gur. So losing or loss of electrons. Oh, I put two E's there, didn't I? Oxidation and the gain of electrons is reduction. Okay, so those are the two that I know. So pick whichever one you like, and just stick with it, and this will help you remember throughout the conversation and throughout your career, hopefully, what oxidation means and what reduction means. So either oil rig, where oxidation is the loss of electrons, reduction is the gain of electrons, or you can remember Leo. Loss of electrons is oxidation, gain of electrons is reduction. So either one of those will be fine. Okay, so hopefully that will help you keep oxidation and reduction state. Okay, and two more terms we're going to learn, the oxidant and the reductant. So oxidant, more commonly called the oxidizing agent. So the oxidizing agent is the agent that promotes oxidation. So it itself is reduced. So that's important to note. So it's promoting oxidation, but it's actually being reduced. Same thing with the reductant, or also called the reducing agent more commonly. So it's the agent that promotes reduction, but it itself is oxidized. So if something is being reduced, then it has to be oxidizing something else. So therefore, it's an oxidizing agent. If something's being oxidized, then it must be reducing something else. So therefore, it's a reducing agent. Okay, in this next section, we're going to talk about assigning oxidation states, and we're going to talk about redox reactions themselves. So the first thing is, when we're assigning oxidation numbers, basically what this is it's a way to keep track of who's gaining electrons and who's losing electrons, or vice versa. Okay, so we're going to do this by assigning oxidation numbers. It's very similar to when you're assigning charge states, almost exactly the same, in fact. Okay, but there are some little differences in it, so we're going to go over how to assign these. First, let's just look at a redox reaction. So here we have zinc, and here we have zinc metal, so zinc solid, reacting with hydrogen, so maybe it's reacting with an acid, to give us zinc 2 plus and then H2 gas. Okay, so suppose if we want to assign oxidation states to all of these. So the first thing you'll see is that zinc metal has an oxidation state of 0, so similar to its charge. So there's no charge on it. It also has an oxidation state of 0. Okay, then we have hydrogen, or a proton you could say. Okay, so we have H plus. So its charge would be plus 1. Well, its oxidation state also happens to be plus 1. Okay, then moving to the right-hand side of our reaction, here we have zinc plus 2, or 2 plus. So it has an oxidation state also of plus 2. Okay, and then we have H2 gas, charge of 0, also an oxidation state of 0. Okay, so suppose we wanted to look and say, okay, well, which one of these is being oxidized and which one of them is being reduced? So the first thing we want to look for is who's gaining electrons and who's losing electrons. So right away, you probably noticed that we're going from zinc 0, and I'll go ahead and write that in just so we can remember, zinc 0 to zinc 2 plus. Okay, so if you go back to your acronyms, what does oxidation means? It means we're going to lose electrons. That's what's happening to zinc. Okay, so here you see it's minus 2e negative. Remember, e negative is the sign for electrons. So here we're losing 2 electrons, so we're being oxidized. And if we take a look at H plus, okay, so it went from being a plus 1, then again, this is 0. Okay, so we're gaining electrons. Okay, so what's gaining electrons? That means we're being reduced. Okay, so here we're actually using 2 hydrogens. Each one of them is getting 1 electrons for a total of 2. Okay, so to go from a plus 1 state to an oxidation state of 0. Okay, and we need 2 of them since here zinc is going from 0 to 2 plus. So we always have to have the same number of electrons moving around. So if we're losing 2 electrons, something has to be gaining 2 electrons. So just like when we talked about conservation of matter, conservation of energy, same concept here. Okay, so if something's losing electrons, something has to be gaining electrons, and it has to be the same number of electrons. Okay, we're not going to create them, we're not going to destroy them, they have to go somewhere. Okay, and if something's gaining electrons, that means they have to be coming from somewhere. Okay, again, we're not just pulling these out of thin air. Now, we can have an electron source, that's fine. Okay, but they have to be coming from somewhere. And generally speaking, we're going to write that as part of our reaction equation. Okay, so here's some rules for assigning oxidation numbers. Okay, so I did that kind of quickly, but now let's go ahead and break down the rules. Okay, so the first thing is elements in their elemental form have an oxidation number of 0. So in their elemental form. What do we mean by that? Well, going back to our example here, we have zinc, which is a solid, and it's just the way you would find it on the periodic table. So you can find zinc on the periodic table just like this. Okay, and then we know that, so it would have an oxidation state of 0. Okay, then hydrogen. Okay, we know hydrogen is one of our diatomic elements. Okay, so H2 is its elemental form. So that's why it has an oxidation state of 0. Okay, so that's our first rule. Any elements in their elemental form have an oxidation state of 0. The next one, the oxidation number of a monoatomic ion is the same of its charge. So the charge of an ion, monoatomic ion, will be the same as its charge, or the oxidation number will be the same as its charge. Okay, so going back to our example here, here we have H plus, so a monoatomic ion, mono meaning 1, atomic just meaning it's an atom. Okay, so it has a plus 1 charge, so it also has an oxidation state of plus 1. Okay, and same thing here. So zinc here has an oxidation charge of plus 2, and also has an oxidation state of plus 2. Okay, so that's our second rule. So the oxidation number of a monoatomic ion is the same as its charge. Our third rule here, nonmetals tend to have a negative oxidation numbers. So nonmetals tend to have negative oxidation numbers, but we can have positive numbers as well. Okay, but generally speaking, just like nonmetals like to form negative ions, they also like to form or also like to have negative oxidation numbers. Okay, so here's a few key ones here. So oxygen has an oxidation number of -2. Okay, and the only time it's going to have something other than -2 is if we're in peroxides. So this is when we have something like HOOH. Okay, so those have a -1 charge, but we're almost never going to see that. Matter of fact, I will never give you that in this class. Okay, next one, hydrogen is +1 when bonded to nonmetals. So if we have hydrogen, it's +1 when it's bonded to nonmetals, but it's -1 when it's bonded to metals. And in this term, we call it a hydride. So we might call this one a proton, we might call that one a hydride. Okay, so hydrogen's, again, kind of a tricky one, but generally speaking, it's really not, if you know these two rules. Okay, so if it's with a nonmetal, it's +1, and it's with a metal, it's -1. Okay, another one that we know for sure, fluorine is going to have a oxidation state of -1. Okay, just like it's always going to, the halogens always want to form -1 ions, well, fluorine is always going to have an oxidation state of -1. Similarly, all halogens have an oxidation number of -1, but the numbers of +1, +2, 3, and +5 are also possible. Okay, but generally speaking, you can assume if it's a halogen, it's going to have an oxidation state of -1, unless you see a funny case. Okay, so there are some exceptions to all of these. Okay, but generally speaking, these are the rules you can go with. This one about oxygen is particularly handy. So if I see oxygen in a molecule, I can go ahead and write -2 there, almost always. And you'll see why that's important when we get to balancing these out. Okay, then hydrogen +1, fluorine -1, and other halogens -1. Okay, so those are going to be like our touchstones, kind of, so to speak. Okay, our fourth rule, the sum of the oxidation numbers in a neutral compound will always be 0. Okay, so if I have a compound and there's no charge written, so that's what we mean by neutral. Okay, so if I don't have a charge written, then the total of the oxidation numbers must be 0. That means if I have something like, let's say water. Okay, and I just said, well, I know oxygen is almost always 2-. That means I need 2 plus charges to balance that out. And of course, we know that hydrogen is always going to be +1 times 2 would be +2. Okay, so for a total of 0. So that's what we mean by that. Next one, the sum of the oxidation numbers in a polyatomic ion is the charge on the ion. So something like sulfate, for instance, or any other other polyatomic ions. So the sum of the oxidation numbers has to be equal to the charge. So just to go with my example here, SO4, we know this is overall 2-. Okay, so for the entire ion, okay, I know oxygen is going to be -2. Okay, so times 4 give us -8. That tells me that sulfur has to be +6. Okay, so this has to add up to a -2. In other words, I need a +6 to balance 6 of these negative charges to leave me with 2 negative charges. Okay, in other words, what I'm trying to say is the total of these oxidation numbers has to be equal to the charge. Okay, so those are your 5 rules for assigning oxidation numbers. And what you'll find is these are very similar to assigning your charge states. So if you can kind of think back to when we assign charge states for ions, very, very similar with very few exceptions. Okay, so here's a list of, I don't know, 15 or so different compounds. Okay, so what would be good practice for you right now is to go in and use those rules and try to assign the oxidation states for all of these. And then I'm going to break them down one by one. So it'd be a good idea to go ahead and pause this and just see what you already know. Okay, so let's take a look at these. So again, one of the best things to do here, and let's just go through these one by one. Okay, so one of the best things to do here is just to find touchstones. So for instance, in this first one, okay, I know oxygen is going to be -2. Okay, so that gives me overall so far oxidation state of -2. Oh, excuse me. Okay, and then I know that each chlorine is going to be -1. Okay, so now any other element in the molecule has to balance it out. Okay, so here we have vanadium. Okay, so vanadium has to balance out a total charge of -2, or total oxidation state of -2, -1 times 3. In other words, we have a total of -3 here. Okay, so 2 plus 3 will give us -5. Okay, and we don't have any charge, so if we did have a charge, we'd see it here. We don't have any charge on this. Okay, so that means vanadium has to balance a total oxidation state of -5. So that means we have to give it a +5. Okay. So it's important to note here, if I was going to ask you the individual oxidation state of something like chlorine, for instance, what you wouldn't tell me is -3. Okay, unless I asked you the total oxidation state of chlorine, meaning, or the total oxidation state of all the chlorines in the molecule. But if I just ask you the oxidation state of chlorine in this molecule, you're going to say -1. Same way that if I asked you about oxygen, you would say -2. Okay, so the individual oxidation states are for one atom only, in other words. Okay, so, but when we're looking to balance the oxidation state out, we have to take account to all of the atoms. Okay, so that means total, we do get a -3 oxidation state from here. Okay, but if I was to ask you just the oxidation state of chlorine, you would just say -1. Okay, so let's check our answer. We've already kind of seen it a little bit. Okay, and there we go. So we said chlorine would be -1. We said oxygen would be -2, again for a total of -5. So vanadium balances out with a +5. Okay, the next one. So here we have copper sulfate. Okay, so this is one of the ones where, remember that copper can have a lot of different charge states. Well, it can also have a lot of different oxidation states. Okay, so here we have to first remember that sulfate, so if we would just isolate sulfate, here we have an overall -2. Okay, so no matter what oxidation states we assign here, we have to total to a -2 for this one. Okay, so we know that each oxygen will be a -2. We're not sure what about sulfur just yet. Okay, so -2 times 4 will give us -8. We want to leave behind 2. Okay, so that means sulfur has to be a +6. Okay, so oxygen is going to be -2, sulfur will be a +6. And I also know that overall they have to be -2 for sulfate. So I know that copper has to be overall +2 to balance the -2. Okay, we can check our answer here. We end up with copper with +2, sulfur with +6, okay, then oxygen with a -2. So notice that even though we had an overall negative polyatomic ion, we still ended up with some positives inside of there. Okay, so sulfur was still positive. Okay, so you could also have done this, well, you couldn't really do this without knowing what sulfate was, because in the end, we're going to have to balance that out. Well, I guess you could, because here you could just say, okay, if I make each one of these -2, it's going to be -8. But then how would you know what these two were. So you couldn't really do that. So part of the balancing this was knowing what sulfate was. Okay, that's the only way you can know. Okay, that copper ends up needing to be +2, and that sulfur needs to be +6 because sulfur is one. Just like with its charge state, it can also have a lot of oxidation states. Copper, just like with its charge, can have a lot of oxidation states. Okay, the next one. We have carbon with 2 hydrogens and oxygen. So this one is sort of an interesting one because we have carbon, we have hydrogen, and we have oxygen. So there could be more than one way of assigning this, but let's just do it the way I've been showing you. Okay, so first of all, we know oxygen always going to be -2, and we've said that hydrogen will just be +1. Okay, so we end up with -2. We have 2 plus 1, so we have +2, -2. This gives us 0. Okay, that means that the only thing left for carbon to be is 0. Because if we assign it anything else, it's going to change the way that hydrogen and oxygen are assigned. Okay, so let's assign this as carbon 0, hydrogen as a +2, oxygen as a -2. And although that doesn't quite make sense, assigning something a 0 oxidation state, that can be. Okay, so we can have carbon as 0, hydrogen as +1, oxygen as +2. And so the reason I say there's more than one way to solve this is we could also do this. So we could treat carbon as a metal. And what I mean by that is, so we can assign 2 minus here. And then we know that if hydrogens are attached to a metal, we give them a -1. So overall we would have -2 plus -2, which gives us -4. Okay, so that means carbon here would be +4. Okay, so that's a second way of assigning it. Just for the sake of you maybe not knowing which way to solve this, one like this I probably wouldn't give you because there is more than one way to answer it. Or I would give you both choices. In other words, the correct answer would be, either, if for instance I was asking you carbon, it would be 0 or +4. But for sake of simplicity, I probably won't ask you ones like that. I just wanted to point out to you that some of them kind of can be funny that way. Okay, so here we've written 0, +1, and -2, and that's fine. Okay, the next one. Here we just have magnesium oxide, or manganese oxide, excuse me, magnesium would be Mg, manganese oxide. Okay, so again, this is one where we have a transition metal, and maybe we don't know what the oxidation state of that transition metal should be. Okay, so we're just going to have to go from what we know. And we know that oxygen is going to be -2, so manganese is our question mark. Okay, so here we have -2 times 7, give us -14. Okay, then we have 2 manganese. Okay, so we'll have to divide this by 2, which will give us -7, basically. Okay, so each of the manganese need to balance out a -7. Okay, so we end up with -7. So that means each manganese has to be +7. Okay, for a total of 14. And just to check ourselves, we can say +7 times 2, which give me +14, and then I have +-14, which would be 0. Okay, so at least it's balanced. Even if I'm not right, at least it's balanced. Okay, let's check our answer. Okay, so +7 and -2. So just what we thought. Okay, so this next one we have osmium oxide. Again, we're dealing with transition metal and oxygen. So maybe we don't quite know what the oxidation state of osmium would be. But we have a good idea what oxygen would be. So we know oxygen is probably going to be -2. So -2 times 4 would give us -8 overall. That means osmium has to balance out a -8. Okay, so osmium here has to be +8. Yeah, if we check our answer, we have +8 and -2. So we were right. Okay, the next one. Let's see, this now we're getting to more complex. So when we just have two things or three things, it's a little bit easier. But now we have a lot of atoms in play here. Okay, so this is where actually writing this out will come in handy. Okay, so again, we know that hydrogen is going to be +1. So we're just assigning what we know. We know that chlorine will be -1. So the only thing we don't know here is platinum. Okay, so we need to know the oxidation state of platinum here. Okay, so we have a +2, or +1 times 2. So we have a +2 here. Okay, then we have -1 times 6, which gives us -6. Okay, so if we say +2 plus -6, this gives us an overall charge, or a charge left over, I should say, of -4. So that means since I have an overall 0 charge on the molecule, platinum has to balance out a -4. So therefore it has to be +4. Let's see what we have. Okay, but see I made a mistake here, didn't I? Okay, so now it says +8. So why is that? Okay, so the mistake I made was that we have hydrogen attached to a metal. Okay, so here I have to deal with it as a -1, not a +1. Okay, so we have -1 and a -1. Okay, so we have -2 plus -6 to give us -8. So that means platinum has to balance out a -8 instead, which makes it a +8. Okay, so don't fall for those traps. Don't just say, oh, I automatically know hydrogen is +1 because, like you just saw, it's not always +1. If you remember back to your rules, okay, it can also be -1 when it's paired with a metal, like in this particular case. Okay, so we have -1 plus 8 and -1. Here we have chromium hydroxide. Okay, so again, we have a transition metal. Don't really know what its oxidation state is going to be. Then we have hydroxide, which is made up of some things we do know what they're going to be. Okay, so hydroxide, remember, is one of your polyatomic ions. Has their overall charge. So we have, this is what we're dealing with, OH -1. So forget about this charge for now. Let's just focus on the charge of our polyatomic. Okay, so assign oxidation states within the polyatomic. We have -2 and plus. Okay, so we have overall -1 here times 4, which gives us an overall -4. Okay, so easy enough. Now we have to remember about our charge on our compound, so this charge. Okay, so if we're trying to decide what oxidation state chromium has, we have to remember this -1. So chromium actually only has to balance out, so we can actually take, say, 4 minus 1 gives us 3. Okay, so chromium has to balance out a -3, and just putting the sign back because I know it's a -3. But I removed it for the math, but I'm adding it back since I know it's really a -3. Okay, so that means chromium has to be +3. Okay, so if I say, for instance, if I go back and I make my total here, so I have -1 times 4 gives me -4. So +3 plus -4 gives me overall -1. And that's the same as the charge on my overall molecule here. Okay, so that's pretty much how to do this. Here it shows you that we did it right. Okay, so suppose I didn't want to sort of do it the way I showed you. How else could I figure this out? Well, I could say x plus -4 gives me -1. Okay, so I could do it that way instead and say +4 plus 4. I would end up with +3. So x equal to +3. Or x is the charge or the oxidation state of chromium. So that's another way to do it. And let's see if we're right. Okay, there we go. So we have a +3 -2 and a +1. So again, remember, if I'm asking you like specifically what is oxygen, what is hydrogen, and what is chromium, you're not going to account for this little the multiplier there. You're just going to tell me for one individual molecule. Okay, the next one, here we have sulfur combined with oxygen. We have an overall -2 charge. So again, we have an overall negative charge. So we have to take that into account when we're assigning our oxidation states. Okay, so we'll start from what we know. Oxygen, we know has to be -2. So we have overall -6 coming from oxygen. Okay, so we have x, so 2x plus 6 is equal to a -2. Or we could say this way. So you could solve that equation if that's the kind of person you are. If you're not that kind of person, then you can say it this way. Okay, so I have overall -6 charge. Okay, so I want to have 2 of them left over. So I'm going to forget about my sign for a second, and I'll just say 6 minus 2 gives me 4. I'm going to add the minus sign back on, because I know that sulfur is trying to balance a -4. And I see that I have 2 sulfurs, so I'll divide by 2. Okay, so each sulfur has to balance a -2. That means sulfur has to be +2. Okay, or solving it the other way around, I could say 2x plus -6 is equal to -2. So add 6, add 6. So you end up with 2x equal to 4 divided by 2, x equal to 2. Okay, so either way you get to the same answer. Okay, so let's see if we're right. Get rid of this. Okay, so we have +2 and -2. So just what we said. Okay, so the next one we have just nitrate ion essentially. So again, we have overall minus charge. So now we want to assign oxidation states for nitrogen and oxygen. Again, we have -2 for oxygen, so times 3 is -6. When you want 1 left over, so that means nitrogen has to be a +5. And nitrogen is one where you might see a few oxidation states. So just trust what the math tells you. Sulfur is kind of the same way. Sulfur might have a few oxidation states that you'll see. So you kind of just have to trust what the rest of the molecule is telling you. Okay, so not a big deal there. Let's see if we were right. +5 and -2, so we were right. Next one, again we have manganese oxide here. But here we're only using 4 oxygens. Okay, so we have to figure out what the charge of manganese is going to be for this one. So same thing here. So now oxygen is -2. Okay, so overall -8. But we want to have 2 left over. So this will end up being a +6. Okay, let's check our answer. +6 and -2. No big deal there. Next one, HPO4. We have 2 minus here. Okay, so we have some variables here. So first, 2 minus, then we have +1 for hydrogen. Okay, so we have -8, and we have +1. Okay, so right now we have overall -7. We're trying to figure out phosphorus here. But we want to have 2 left over, so we'll just add 2 to that. So we end up with -5 to balance. So phosphorus here has to be a +5. Okay, we can check our answer for that one. Okay, so +1, +5, and -2. Next one here, cadmium oxide, or cadmium sulfide, excuse me. Okay, so here's one where maybe we don't know what the oxidation state of either of these should be. Okay, so we have to kind of go back to what we learned about charge. So remember things kind of close to oxygen, those ones are going to want to tend to be a -2. So just like the halogens tend to be -1. Okay, so here we'll assign sulfide as -2. That means cadmium has to be +2, and that's the right answer. Okay, so unless sulfur is in a situation like, we don't have one on the screen, but notice here, Sulfur here was +2, but now we're assigning it -2. Okay, so depending on the situation, you may have some of these elements that change their oxidation state, and they're not always in the same oxidation state, not even the same plus or minus oxidation state. Okay, so just sort of trust what you know. Next one, aluminum hydride. Okay, again here, normally we would sign hydrogen as a +1. But remember, if it's with a metal, like it is here, it's going to be -1. So -1 times 3 gives you -3, which means aluminum has to be a +3. And that's generally the same charge that we've said for aluminum. Remember, aluminum we have said is almost always +3. Okay, so again, easy to assign it here. Okay, so let's check ourselves. We said +3 and -1. Okay, for overall +3 and -1. Yeah, good. No big deal there. Okay, a little bit bigger one now. Now we have sodium, chromium, and oxygen all put together. Okay, so again, but it's just the same thing. So just assign what you know. -2, we know sodium is going to be +1. Okay, so -2 times 7 give you -14. Sodium +1 times 2 will give you +2. Okay, so overall, we're left with -12. Okay, we don't have any overall charge here, so that means these two chromiums have to balance this. So divide by 2 gives us a -6. See, so each chromium has to balance a -6. So here we'll say that chromium is a +6. And if we check our answer, that's exactly right. I think that's the last one, yeah. Okay, so I'll leave these up for a second, so in case you want to check your answers on your own. Okay, so make sure that you know how to assign oxidation states rather quickly. Okay, these will be just one part of a bigger problem, generally speaking. So do make sure that you can assign these. I have a good worksheet I can put up for you guys regarding this, and I'll go ahead and add that to the Blackboard for you. Okay, so let's move on to the next section. In this section, we're going to talk about balancing redox reactions. So now we've learned to assign redox numbers, or oxidation states, I should say. And now we're going to balance these actual equations. So the first thing I'm going to do here is just show you a method how to balance the equations. And then I have 5 or 6 examples, and we'll go through them one by one. Okay, so first, let's just talk about what this method is. So this method is called the half-reaction method. And what this does is you treat each redox reaction on paper only, so it's not like we're really splitting the reaction, but you treat it as the oxidation and the reduction as 2 separate processes. Okay, then you balance each one of the half reactions. Okay, then you recombine them to attain a balance equation for the overall reaction. Okay, so we're going to use the half reduction method. And how does this work? So just first we'll go over the rules, then I'll show you an example, and then we'll work some together. So the first one we're going to do, or the first thing we're going to do is we're just going to assign oxidation numbers to determine what was oxidized and what was reduced. So just like we did. So assign oxidation numbers. That's your first step. Okay. Next, we're going to write separate oxidation and reduction half reactions, and I'll show you what those are. Okay, but essentially it's taking everything that's involved with oxidation, taking everything that's involved with reduction, and just writing them separately. Okay, then balance each half reaction. Okay, and you're going to do this a special way. So you're going to balance elements other than hydrogen and oxygen, and you'll see why. Then you're going to balance oxygen by adding water, balance hydrogen by adding H+, and then balance the charge of the half reaction by adding electrons. Okay, so I'll give you a second with these still up here to write them down. You can pause if you need to. Okay, so step 4, multiply the half reactions by integers so the electrons gained and lost are the same. In other words, if I have, well, we'll see how to do this, but basically you want to even out the electrons gained, the electrons lost by just multiplying either both or one of the half reactions by an integer, so just a whole number. Okay, then you'll add the half reactions, canceling species that are identical on both sides. So if it's on both sides of the arrow still, you can cancel it out. Then make sure the equation is balanced according to mass. So that's still number one important, very important. Has to still abide by conservation of mass. Then make sure the equation is balanced according to charge. And I'll give you a second. Okay, so let's look at let's look at an oxidation reaction, or redox reaction, I should say. Okay, so here we have manganese oxide combining with C2O4, okay, to give us Mn2 plus and CO2. Okay, so first of all, we're going to start out by just assigning oxidation numbers. Okay, and you're going to do this exactly the same way. Okay, so again, you're going to go in and you're going to say, okay, I know this is -2, -8 for overall, -1 still, so this has to be +7. So exactly the same way you did it before. Okay, so I'm just walking through this as an example, so I'm going to kind of expedite the process a little bit here. Okay, so here we have manganese going from +7. We have carbon as a +3. Okay, then we have manganese going to a +2. Okay, we have carbon going to a +4. So the first thing we need to do is decide after we assign oxidation numbers, figure out what was oxidized and what was reduced. Okay, so here we have manganese going from +7 to +2. So clearly it's gained some electrons. So clearly this is the one that's being reduced. Okay, then now we have carbon going from +3 to +4. So clearly it's being oxidized. Okay, so look for what's gaining electrons, look what's for losing electrons. Okay, so manganese is being reduced, carbon is being oxidized. Again, because manganese is going from +7 to +2, carbon is going from +3 to +4. Okay, so manganese is clearly gaining electrons, carbon is clearly losing electrons. Then here we say manganese is being reduced, carbon is being oxidized, and that's true. Okay, so next thing we want to do, we want to write half reactions. Okay, so we'll start out by writing the oxidation half reaction. And you can start with the reduction half reaction. It doesn't really make a difference. But here we're going to start with the oxidation half reaction. So all this means is we're going to gather up everything that's involved with the oxidation reaction. So if we go back to our example here, so everything that's involved with oxidation here, okay, we're going to say this compound, so our carbon compound, and CO2. Okay, why? Because here we have carbon +3 to +4, so that's the oxidation, of course. But these are both species involved with the oxidation of carbon. So those are the things we want to bring along to our half reaction. Okay, so if we're going to write this out, we're going to write chromate going to CO2. Okay, so that's our whole oxidation half reaction. Now we want to balance this. So you can go ahead and write the reduction one now, or you can go ahead and start balancing now. Either way you want to do it. But let's go ahead and balance the oxidation portion. Okay, so first balance the carbons. And here we're talking about just balancing by mass. In other words, we have 2 carbons coming in, but only 1 carbon coming out. So we have to balance that. So first we need to add a coefficient to CO2. Okay, next balance oxygen. It's already balanced, good. Okay. Now, last thing, we need to balance the charge by adding electrons. Okay, so on this side we have overall 2 negative, so 2 electrons here. So we need to balance that out. Okay, so we have a -2 on this side. So we need to balance that out. So here we have 0 overall charge. So we need to balance that out by adding electrons. Okay, so we'll just add 2 electrons to our right-hand side. So now charge over here is -2, Charge over here left is a -2. So they're equal to each other. Okay, so that's balanced. It doesn't have to be 0. In other words, I don't have to try to get the charge on my left-hand side equal to 0 and this equal to 0. No, that's not what I want to do here. I just want to make it so that the charges are the same. Okay, so on the left-hand side is -2, so I'll add 2 electrons to the other side to make it also -2. Okay, so that would be your balanced half reaction for oxidation. Now we want to do the same thing for the reduction. Okay, so this is our reduction half reaction. Again, just grabbing everything that's involved with reduction. Okay, so here we have MnO4 and then manganese 2+. Okay, so first step, balance the half reaction. So balance it just by mass. Okay, so manganese first. Turns out it's already balanced. We have 1 manganese coming in, 1 manganese coming out. Easy enough. Okay, now we need to balance oxygen. So remember, we don't balance oxygen by just adding a coefficient. That's not what our rules say to do. No, our rules say to add water. Okay, so every water gives you 1 oxygen. So I need to balance 4 oxygens. Okay, so 4 oxygens. So I'll just add 4 waters to the other side. Okay, so now on each side I have 4 oxygens. Okay, but now I've added hydrogen. Okay, so I've added hydrogen, for 8 of them actually. Okay, so now I don't have any hydrogen on the other side. Okay, so I'm going to balance that out by adding H+. Okay, so I'm not going to add more water, I'm not going to add H2, I'm going to add just H+. So now, on each side I have 8 hydrogen, and here I have 8 hydrogen. Okay, so they're balanced. Now last thing, remember, yeah, and just a note here, since I'm adding H+, this is going to be considered to be the acidic solution balancing. Okay, and we'll look at balancing in basic solutions as well. Okay, last thing we have to do, balance our charge by adding electrons. Okay, so this part it gets a little tricky. Okay, so on our right-hand side, we have overall 2+, and here if we were to balance everything out, we have an overall 7+. Okay, because we added H+, remember? So 8+ and then just a -1 would give us overall 7+. So what I'm going to do here is maybe not quite what you think. So I'm going to add electrons to balance this. This is my only way of balancing the charges, just by adding electrons. So what I want to actually do here is I want to make +7 equal to 2+. I want to make those two equal. And the way I can do this is by adding 5 negative charges. So 5 minus charges plus 7 will give me overall +2, would be equal to +2. Okay, so add electrons to the positive side to actually bring its positive charge down so that it's equal to this. So we want to make them both +2 on each side, in other words. Okay, and the way I can do that is just by adding 5 electrons to each side. So I'll kind of go over that again, because I think this is the part where that gets a little bit confusing. Okay, so if I'm looking at this, overall I have +2 on this side, so my charge over here is +2. Here I have a -1, 8 times +1, which gives me 8+. So 8+ plus -1 gives me a +7. So +7 and +2 obviously aren't equal. So what I want to do is I now want to add electrons to balance this out. So what I'll say now is, how can I make +7 equal to +2? Well, I can do that by adding 5 more negative charges. So what I end up with this is this. So I have 8+ plus -1, again that's -7, but if I then add +5 electrons, so 5 negative charges in other words, this is going to give me overall +2. Okay, so remember what I'm basically saying is here is I'm adding -5. So I'm adding plus -5. Okay, so for overall, -6 plus 8 gives me -2. Okay, so I end up with +2 on this side and +2 on that side. So in terms of charged, I'm balanced. Okay, now I want to multiply the half reactions by integers so that the electrons gained and lost are the same. In other words, I want to balance out these electrons and these electrons. And the way I'm going to do that is I'm going to do that by multiplying either both reactions, both half reactions, or one half reaction by a number so that they're equal. In this particular instance, I have 2 and 5. Okay, so there's really no way to balance 2 and 5 except to multiply both equations by something. So in this case, I'll multiply this equation by 5 and this equation by 2. So that would give me a total of 10 electrons on each. Okay, so multiply by 5, which will give you this. So 5 chromate, 2 minus, plus 10 CO2, plus 10 E negative. Okay. Multiply the other one by 2. So sometimes you'll see that. So in other words, this coefficient and this coefficient, sometimes you just swap them. Sometimes it works out that way. And this is one where it works out that way. So multiply the other one by 2. So this gives me 10 electrons on this side, 16 hydrogen, and you can do the rest. Okay, the important thing in here is that I'm left with 10 electrons and 10 electrons. That's my most important thing. Okay, now I'm going to add the half reactions, canceling the species that are identical. What I mean by that is, here I have 10 electrons, 10 electrons. So remember, if you noticed in our balanced, or in our just reaction before we balanced it, there were no electrons pictured in that reaction, none of them written out. So we know that it's a redox reaction, so we know that the electrons are moving around, but we don't actually write them. Okay, this is why. So in the end, we just cross them out. Okay, we can look for anything else that can be crossed out. So any hydrogens, no. Okay, do we have any manganese oxide? No. Bromine on either side? No. Manganese? No. Okay, so basically that's all we can cross out. Okay, so you can add them together and then cancel out, or you can cancel out before you add together. Whichever way you prefer is just fine. Sometimes it works out better to add and then cancel out. Okay, so you can have just one big long equation. That's probably the best way to do it. And then you'll end up hunting for things that are the same. So here we see 10 electrons on both sides, so we just cancel those out. Okay, so in this particular case, we didn't cancel before we added. And honestly, that's probably the better way to do it. Okay, and then you end up with, then you just rewrite the equation and you end up with your balanced equation. Okay, but don't forget your last step. Make sure the equation is balanced according to mass. This means make sure that I have the same number of hydrogen, the same number of oxygens, same number of all the different molecules on both sides, or different atoms on both sides. Okay, so just like we did before. Okay, so just make sure all the masses are balanced, just like you would balancing any other equation. Okay, so that would be your final answer. Okay, and of course make sure it's balanced according to charge. Okay, so once we have the masses, then make sure the charge is balanced. So we have 2 times minus 1, 2 times plus 2, and then 5 times minus 2. So there's a lot of stuff going on here. So just make sure it's all balanced out. End up being both plus 4 on both sides. That's fine, as long as they match. Okay, so that would end up being your final answer. And again, since we have this in H+, this would be considered the acidic solution, or the solution in acidic solution. Okay, so what if we're balancing in basic solutions? Okay, so it just changes one step right at the end. It's the same process, except in the end, you need to neutralize the H plus by adding OH minus. Okay, so if the reaction occurs in basic solution, balance it as if it occurred in acid first, so do the exact same process. Once the equation is balanced, add OH to each side to neutralize the H plus. Okay, so neutralize the H plus in the equation to create water in its place. So for every H plus and OH minus that you can combine, they just form as water. Okay, if this produces water on both sides of the equation, then you can cancel it out because it's on both sides. Okay, so exact same process, only this time you have to balance it at the end with OH minus. Okay, so if we take our same example that we had before, okay, we balance this one in acid. Okay, but suppose now we want to balance this in basic solution. So what you need to do here is just look for anywhere where you have excess H plus. And anywhere you have excess H plus, you're going to want to add OH minus. So here we have 16H plus, so we need to add 16 OH minus. Okay, and whatever we do to one side to make that okay, we have to add to both sides. Okay, so we're going to have to add 16 OH minus to both sides. Okay, and that gives us this. Okay, so we end up with 16 OH minus plus 16H plus gives us that equation, and then plus 16 OH minus on the other side. And one thing we have to do here is we need to combine OH minus and H plus to give us H2O. So this would give us 16H2O. Okay, so that's what that step meant. Okay, so combine those to give you 16H2O. And then on this side, notice we're just keeping them the same. They just bring them on down. Okay, so 16OH minus plus 16H plus gives you 16H2O. If, for instance, we for some reason still had, I don't know, let's just say 2H plus over here, you would combine those with 2 of the OH minuses to give you water. Sometimes that will happen. Okay, but in this particular case, we don't have any there. So just bring down your OH minus. Then the last thing is we're going to look for water on both sides. So water's here and water's here. Okay, so we can cancel them out. Okay, so subtract 8H2O from each side. In other words, cancel 8 here. So cancel 8 here, which will leave you with 8. Okay, so your new equation, balance and basic solution, becomes 8H2O plus 2NMNO4 plus chromate gives you magnesium oxide plus 10CO2 and then 16OH minus. Okay, so it's essentially the same solution, only this time we're balanced in a basic solution instead of being balanced in an acidic solution. So you did everything exactly the same until we get to the end, and then we just need to remove the H plus by adding OH minus to both sides, cancel out anywhere where we can cancel out water, okay, and this gives you your new equation balanced and basic solution. Okay, so now you've seen an example. So I want you to go ahead and try one on your own. Okay, so here we have just another equation. So it's unbalanced. So go ahead and take some time, walk through the rules, look back at the example if you need to. You can even rewind and do the steps with me, just with a different equation if that will help. Okay, but now I'm going to pause. I'm going to let you pause the video and try to work this one out. And when I come back, I'll work it out with you. Okay, so let's try to work this one out together. Okay, so first step, we want to assign oxidation states and just try to figure out what's being oxidized and what's being reduced. Okay, so first thing here, we have to decide oxidation states for each atom here. Okay, so oxygen is going to be -2 times 7. Let me grab a pencil. Okay, let me pause for a second here. Okay, so let's try to assign oxidation states. So just same as before, oxygen will be -2. So times 7, that gives us -14. We need 2 left over. Okay, so let's add 2. So -12 divided by 2. That means each of the chromium has to balance out -6 charge. So each one's going to be +6. Let's get rid of that because we don't need it anymore. Okay, then oxygen here, again, -2 times 2 gives you -4. Hydrogen we know is going to be +1. So nitrogen here has to be +3. Okay, chromium, it's written here, so we already know it's +3. This one's easy. Okay, now we have nitrate ion. Okay, so -2 times 3 will give us -6. +1 gives us -5, which means nitrogen has to be +5. Okay, and notice here they're asking us to balance this one in acidic conditions. Okay, so usually it will say acidic conditions or in basic conditions. Okay, so now we need to decide what's being oxidized and what's being reduced. Okay, so let's just make our pairs here. So first of all, I see that chromium is going from a +6 to a +3. Okay, so it's gaining electrons, so it's being reduced. Okay, then what else do we have? We have nitrogen going from +3 to +5, so it's being oxidized. Okay, so now we need to write out our half reactions. Okay, so let's just write these out. Okay, so first write out your half reactions. And I'm just going to write them both out here. Okay, so I see Cr2O7, 2 minus, and anything else that's involved with the reduction. Okay, so this is going to Cr3 plus, so +3 chromium. And there's nothing else involved with it. Okay, so this would be my reduction half reaction, and then my oxidation half reaction would just be HNO2 going to NO3 minus. Okay, so those are my two half reactions. Now I need to pick one and balance it. Okay, and you can choose either one. It really doesn't make a difference because in the end, you're going to combine them anyway. Okay, so I'm going to slide this up. We don't need the full equation anymore. Okay, so let's start with, I don't know, let's start with the reduction equation just because I wrote it first. Okay, so I'll just put a line here and we'll come down below. Okay, so we rewrite our equation. So Cr2O7, 2 minus, goes to Cr3 plus. And I'm going to slide this up again because we just don't need those anymore. Okay, so try to maximize what I can show you at a time. Okay, I just realized I made a mistake in this. Okay, so this happens even to me. Okay, so here I added water to this side, okay, in order to balance out the oxygen. But remember, I actually need to add water to this side to balance out this oxygen. Okay, so I'm going to reset and we'll work through this again. Give me just a second. Okay, so now we'll reset. Let's try this one again. So if you were wondering, wait, why did he do that? Why did he add it to that side and not the other side? Well, you were right. Okay, so I just made a mistake there. So let's give this one another try. So we have HNO2. Okay. So here, again, just like I was trying to say before, we have 2 oxygens and 3 oxygens, so that means we need to add H2O to this side. Okay, so just one H2O to balance out that one oxygen. Okay, that makes a lot more sense, right? Because now we have 3 oxygens and 3 oxygens. And remember, we didn't have to do anything to balance our nitrogen because there was only one on each side. Okay, so now let's rewrite our equation. Now we end up with H2O plus HNO2 gives us NO3 minus. Hey, I'm glad I caught that because that would have changed our entire answer in the end and it would have been completely messed up. Okay, so for now we didn't lose too much, right? Okay, so it's always okay to start over if you make a mistake that way. Okay, so now we need to balance our hydrogens. Okay, so here we have H2 and H, so we have 3 H plus. Let me rewrite in red. So here we have 3 H plus. On the other side we have no hydrogens. Or just 3 H's, we'll say. Here we have no hydrogen, so we need to say plus 3 H plus. Okay, we'll get rid of that, and let's rewrite our equation. So now our equation becomes H2O plus HNO2 gives you NO3 minus, looks more like a W, doesn't it? NO3 minus plus 3H plus. Okay, so now we should be balanced in terms of oxygen, hydrogen, and nitrogen. So in terms of mass, we're completely balanced. So the next step is to balance in terms of charge. Okay, so first we need to determine our charge on each side. So on our left-hand side, we have water plus HNO2. So we essentially have 0 charge here. Okay, but here we have -1 plus 3 positives. Okay, so for overall here we have +2. Okay, so in order to balance a -2 and a 0, best thing to do here is just to add 2 electrons. Okay, so that'll give us overall Okay, so that will give us the overall. Now, if we say redo this math here, we have -1, we have a +3, and then we have +2 negative, 2 minus charges in other words. Okay, so we have 3 minus plus 3 positive, so this would overall give us 0. 0 and 0 equal. Okay, so that gives us a balanced charge there. Okay, so just to rewrite our equation here, so this becomes H2O plus HNO2 gives me NO3 minus plus 3H plus 2E minus. Okay, so this is our final oxidation half reaction. Okay, now what we want to do is we want to take both of these and we'll move on to our next step. So I'm going to set up a new sheet of paper. Okay, so now we have our two balanced half reactions copied close to each other, and it would be best to just write these on a new sheet of paper. Okay, and now we can finish balancing these. Okay, so the next step, now we need to multiply by an integer to make the electrons in the same as the electrons coming out. Okay, so in our first one here, we have 6 electrons coming in, and our second one, we have 6 electrons going out. Okay, so what we need to do is we need to find some integer that will give us the same number of electrons coming in as we have coming out. So here, probably the best thing to do is just to multiply the second one by 3. Okay, because that will give me 6 coming out. I have 6 going in, 6 coming out, easy enough. Okay, so what I'm going to do now is just rewrite the equations down below. Okay, so just draw a line here. So I end up with 6E minus plus 14H plus CR. Oh, I lost the R somewhere, huh? 07, 2 minus plus 2CR plus 7H2O. And on the bottom now we have 3H2O plus 3HNO2 gives me 3NO3 minus plus 9H plus 6E minus. Okay, so now what we need to do is first check, okay, I have 6 electrons coming in, 6 electrons going out. Good. Okay, so now I can add these equations together. Okay. Then I can cancel out anything that appears on both sides. So we'll write it like this. And these get a little bit long when you write this part, but just bear with it. Okay, so 6E minus plus 14H plus CrO7 to minus, and then what's on the bottom? Oh, I lost my arrow, huh? Where did I lose my arrow? This should be my arrow. Okay. Oh, sorry about the turning there. Okay, and then so that will put me up to this point basically. Okay, and then I'll grab what's on the bottom. So plus 3H2O plus 3HNO2. Okay, and again, that gives me up to this point. So now I'll go to the other side. Okay, and I'm just going to write it down below because it's a little bit easier in terms of space. So draw your reaction arrow, and now draw the other, or write the other side. Okay, so I'm going to give myself a little more room than that. So 2Cr3 plus 7H2O, and then grab what's on the bottom, plus 3NO3 plus 9H plus 6E minus. Okay, now we can cancel out anything that's the same on both sides. Okay, so first we know 6E negative, that would be the same. Here I have 9H plus. Okay, and over here I have 14H plus. Okay, so that will leave me with 5H plus. And then I have chromate, no chromate on the other side. Water, here I have 3 waters, here I have 7. So that will leave me 4H2O. Okay, then HNO2, don't have any other of those. Okay, so my new equation now becomes 5H plus Cr of 7 to minus plus 3HNO2 gives me 2Cr 3 plus 4H2O plus 3NO3 minus. Okay, then our last step, we need to just make sure that we need to make sure that our mass is balanced, make sure that our charges are balanced on both sides. Okay, so there's our mass balance. So I went ahead and paused and went ahead and wrote that out for you. Okay, but you can see we have the same atoms and the same number of atoms on each side. Okay, so our mass balance is good. Now we need to figure out our charge balance. Okay, so ideally, our charge should be balanced on both sides as well. Okay, so our charge balance here, we have 5 times plus 1. So we have 5 times 1 plus minus 2. Okay, I believe that's everything for this side. Okay, so this would ultimately be essentially 5 plus minus 2, 5 minus 2, basically plus 3. Okay, and on the other hand side, we have 2 times 3 plus minus 3. My tablet's starting to get a little unresponsive here. Maybe I'm just rushing a little bit. I don't know. Okay, so I end up with plus 6 plus minus 3, which basically gives me a plus 3. Okay, so our charge is balanced, our mass is balanced. Okay, so ultimately this is a good balanced equation. So this would be your final answer. And remember, this would be an acidic solution. So this is an acidic. The reason we say it's an acidic is because I have H plus left over. Just a point of note here, I went ahead and fixed it, but I did miss this 2. Okay, so just make sure you know that that's Cr2O7. That changes your mass balance there. Okay, so again, I will print these and post them onto the Blackboard for you. I noticed in the playback that me zooming out like this really didn't help you guys that much because it's really not all that clear. So I think the better option would just be to go see the PDF that I'll post for you. Okay, so coming back to the slides. Okay, our next problem. Okay, so this is where we'll pick up. I think this is a good place to stop, just for now. So now you've seen the setup. Now you've seen one worked out. Here's another one for you to try in the meantime. In the next video, we'll pick up with this. And I think what I'm going to do is maybe just make a video of only solving the next, 4 or 5 problems and put that up separately. That way you can just jump right to it and work these out that way. But next time we will continue working out these problems and we'll finish up the chapter.